Okay, perfect. So I'm live. So yeah, let's just do this. So here's kind of my agenda for this. So exam, it's Monday, 7 a.m. until 2 p.m. So there'll be about 20 questions that mostly fill in the blank. There might be a few Verilog questions where you'll have to like make like a state machine and then turn that in. So like use the simulator, make sure it works. What?
Sorry, that was my mic.
No problem. And then, yeah, so this video is recorded. So I will send Clint the link to it on YouTube, but we're going to take it down before the exam starts. Just, that's not my rule, that's his rule. So we'll just do that. Then, yeah, Real Digital, you'll have access to that. And almost everything I got for this presentation is from there anyways. So if you have any questions, you can go into more detail on there come exam time. So yeah, I'm gonna go over kind of all the stuff before exam one first, then we'll dive into all the new material after that. So I plan on going till about 9 o'clock unless there's more questions and we can keep going. So let's just get started then. So transistors. So we have CMOS technology, and so that stands for like complementary MOSFET technology. And so they use NFETs and PFETs to make up different circuits. And so here's the NFET, there's the symbol. So it passes a 0 well and it turns on with a 1. So when we put a 1 right here on the gate, then can you guys see this? There we go. So when we put a 1 on the gate, then this guy is kind of closed, just like a closed switch. And then the PFET's the opposite. So when we put a 0 on the gate, then it's going to pass that 1 through it. So with CMOS, we can make different types of structures. So we have like inverters, NAND gates, and NOR gates. Then we can combine the inverters and the NANDs and the NORs to make the AND gate, which is just a NAND with a NOT. Then the OR gate, which is just a NOR with a NOT. And so here's all the different truth tables. And so the reason that we do this kind of complementary pair is so that the output is always driven. And so we never also short VDD to ground because that would destroy the FET. And so you'll notice kind of there's like a parallel structure up here and a series down here. Here's a series in parallel. And so it kind of always has this, which I'm sure you're all familiar with. And so here's just like a quick AND gate, just to kind of show how this guy works. So
Logan,
like,
sorry to interrupt. Can
Yep.
I get the meeting link for this? There are some people who want to join.
Oh yeah. Let me see that quick.
So is this exam going to have questions from our previous exam? Because I believe those CMOS related questions I definitely saw in the first one.
Yeah, those are on the first exam. There'll be a little bit of review. There might not be CMOS, but he never sent me the final version of the exam. So I have like last year's final exam. So there might be some CMOS. It's going to be more heavily KMAP focused. I'm just kind of, yeah, covering all the bases. In case it does come up, you have something.
Sure, awesome.
So there's
All
a
right.
Zoom link.
Thank you.
And then let's get back to this. So also I cannot see the chat because I only have one monitor up right now. So if you have any questions, like please just cut me off and ask something. Okay. Yeah. With the AND gate, this is just review, but like if we had like a 0 and a 0 here, so we'd have a 0 at this point. So this guy would turn on. And on here, we have a 0. So this guy would turn on. And our output would be connected to there. And then right here, A would be a 0. So this one's off and this one's off. So you see the output would be high, which corresponds to this state right here, 0, 0, 1. So different types of gates that we have. So yeah, here's like all the CMOS stuff. And so here's the corresponding symbols. So we have like the inverter, the NAND gate, NOR gate, AND gate, and OR gate. And so what's interesting is that these are the exact same gate. They have the same truth table. They're just drawn differently. And so kind of in general, so if we had like a circuit like this, like this is the same thing as if we did this guy. This is an OR gate now. So if there's a bubble, put a wire. If there's a wire, put a bubble, and then switch the shape, and you get the equivalent circuit. So kind of all of them use that exact same rule to get between the two. And then the XOR gate, so this one's special. So it always outputs a 1 when an odd number of inputs are asserted. So if A is 1 and B is a 0, then it's a 1 on the output. And if B is a 1 but A is a 0, then it's a 1 on the output. But if they're both 0 or they're both 1, the output is a 0.
Logan?
Yeah.
Quick question. Do you have the PowerPoint available or somewhere we can get the PowerPoint?
Yeah, I probably can make the PowerPoint available.
Okay.
I think that'll be fine. There's no test questions on the PowerPoint. I just use the test questions to make it.
Oh, okay, okay.
So that should be good.
All right.
I'll double check with Clint Cole about it, just to double check, because I don't want to be mad at me. So,
Oh, okay. Yeah, that's all right. That's all
yeah,
right.
I'll send him an email with the PowerPoint and be like, hey, can I share this? And if he says yeah, then I'll totally get that sent out. No problem.
All right. Thank you so much.
So yeah, here's the XOR. So that's the schematic symbol. It looks like this if you make it with and or not gates. So moving on. So we have POS and SOP circuits. So this is how we use these gates to make logic circuits. And so with POS, we have one AND gate and a bunch of OR gates. And so here's how the equation looks. And then SOP is the opposite. So we have one OR gate and a bunch of AND gates. And so the way like the SOP works is like when you OR values, like let's say we had like this right here, 0, 0, 1. When we take the OR of 0, 0, and 1, then the output's going to be a 1 because at least one of them is a 1. So what we're doing is we're saying for what combinations should we get a 1 on the output, and we just make the AND gates like appear as they should. And the POS is the opposite. So all of these have to be 1s, right, for us to get a 1 on the output. So if any one of these is a 0, then the output's going to be a 0. So that's kind of how they work. And so the way we do the POS is we look for max terms, which is when the output is 0, and SOP we look for the min terms, which that's when the output is a 1. So I have an example of that on the next slide with K-maps. So kind of the rules for K-maps, you have to circle your terms in square rectangular boxes, and you have to circle a power of 2 elements. So like you can't circle 3, that doesn't count. You have to be like 4. So with SOPs, you circle the 1s, and then with POS, you circle the 0s. So I'll just do this one real quick on the left. So an SOP right here, I could do something like this for the first circle, and then I have a loop around here, right? And then I could do one like that. And for the POS, so this is like SOP, this one's POS. So with the POS, it's just the total opposite. So I could circle the 0s like this. It'd be one of them. I could do one like this. And I guess I could also do kind of this one right here. So you always, yeah.
So with the SOP circuit, wouldn't you want to loop the most possible? So for the top one, wouldn't you loop it with the bottom?
Yeah, good catch, good catch. I didn't see that. Yep, so loop as many as you can, and you can wrap around the edges. I think I did it correctly on the POS. And so here's kind of an example. So if you're given an SOP circuit, then like, if you're given this truth table, can you make a minimized SOP circuit? So the first thing you want to identify kind of where the 1s are. So that happens at min term 1, 3, and 5, just because like this is 1, this guy's 3, this guy's 5, right? And then we just put them in the table. So we see 0, 0, 1. This goes into 0, 0, 1. So we write the 1 right there. And then this is 0, 1, 1. So that goes here. And this one is 1, 0, 1. So it goes there. And then all the other ones are 0s. And so then we do our loops, and just like normal K-map stuff. So we look at what variables do not change. And so like on this top loop, we see that A is a 0 the whole time and C is a 1. And so oh, this is another mistake. That should be A and C right there. And then this one right here is, we see that B is always a 0 and C is always a 1. So that's the B naught and C. And then, yeah, so I fixed that one. Okay, so here would be this circuit right here. If we just take the OR of that guy and that guy like this, then we get this circuit. And so one more thing we can do to minimize it is you see, like, if we count the number of gates here, this NOT gate has 2 gates, this one has 2, AND gates have 6, OR gates have 6, right? So that's a 22. But what we can do is we can insert like 2 NOTs right here, and that doesn't change the operation at all. But now this is a NAND gate, so it's only 4. This is a NAND gate, so it's 4, and this one is also a NAND gate. So that's 4, and then we have 2 and 2, so that gives us 16. So that's how that works. And then same thing with POS. So we just look for the zeros, pop them in the table. So yeah, 0, 0, 0 goes there, 0, 1, 0 goes there, etc. And then make your loops. And then once you have your loops done, then we have kind of these 2 things. And so it's the same thing. You can just minimize this circuit by moving these NOT gates into just inverters right there. So this would be, of course, a NAND gate. So that one's 4, this one's 6, and this one is 6, 6, 2, 2. So kind of any questions on that, on just like simple K-maps?
Not necessarily K-maps, but more about going from the diagram to the equation, the SOP equation. Can you go over a bit about how to go about simplifying, like some things to look out for?
So do you mean like if you're given
Like we're given a drawing, like
this?
yeah, something like this, and we're supposed to simplify. Do you have any like tips or tricks to like? Because I know at some point it's just you just gotta grind it out. But
So I think the easiest way to do this is to go from here to a K-map, then go from K-map to a new circuit. It's really hard to kind of visually see what's going on. But what I do here, so I look at this term. So this one is A naught or B naught, right? Or C naught. So this is like the first term. And you see that right here, right? The A naught or B naught or C naught. And so if you just edit, like, let's look at this one right here, right? So this one, we see this is what? We have an A. So this wire is A. This middle wire is B naught. And this bottom wire is C. So that's going to be A, B naught, and C, like that. So you just have to kind of look at what they are, get the equation, and then once you have the equation, you can go straight to the truth table. And I have another example of that coming up. So does that answer your question?
yeah, so it's you want to convert the equation, like the SOP equation, to a truth table, which will make it easier to simplify.
Exactly. So
Okay.
once you need to get it to a K-map to perform like the simplifying process. So you should always try to, if you start with a truth table, put it into a K-map. If you start with a circuit or an equation, then convert that into a K-map. And then once you have a K-map, then you just have to perform the normal rules and find the final minimized equation.
So yeah, the K-map's basically the key. That's basically just the key that you need to minimize the circuit.
Yeah, exactly. So once you have the K-map, like, you're golden. And so one more thing I forgot to say this. You'll see that we made like minimize, let's look at these. These are both minimized SOP and POS circuits, but in this example, the POS is better. And that's just was kind of dumb luck. It depends on the circuit. You really don't know what it's going to be at first. Like in this example, like we have 5 different outputs that give us a 0. Well, 5 different inputs give us a 0 on the output, but the POS was still small. So you have to kind of do the SOP and the POS if you want to find like the most optimal circuit you can possibly do. And in practice, you don't do this. You just put whatever equation you have in to Verilog, and then you let the tools automatically minimize it for you. So going back.
Also,
Yep.
Logan did mention it last time in our review that if you have two what's it called? 2 little dots next to each other, they do cancel out.
Oh, yes, that's a good point. So like if we had something like, yeah, so if we had, here's an example right here. See these 2 dots right here? That's equivalent to here with no dots. So exact same thing, just because it's like a not is nothing. Because a not inverts it one time, the other one inverts it back. So if you see 2 bubbles, you can just eliminate both of them at the same time. So that's a good point. So let's see. So here's like an equation to K-map kind of example. So with this one, we'll see like if A is a 1, B is a 0, and C is a 1, then the output's going to be a 1. And so like this is an SOP circuit, so this is how it works. So if we look for the 1, 0, 1 spot, that's right here. So we put a 1 there. This one would be 0, 1, 1, which is here. And this one is 0, 0, 1, which is there. And then all the other ones are going to be 0. And so once you're there, then you do your circles and you're done. You get your final equation.
Or
so
oh, you're doing it right now. Cool.
Then like this one, the POS, it's very similar. So what we're doing instead, we're looking at like what terms give us a 0. So like this expression equals 0 when A is a 1, B is a 1, and C is a 1. Because we're doing like not A, so not A is 0, or not B is a 0, or not C is also a 0. So it gives us that. So it's kind of like the SOP method I just did, but you flip it. So we look for 1, 1, 1, and that's a 0. And then this one would be 1, 1, 0. So 1, 1, 0 is here. This one would be 1, 0, 0. And then this would be 0, 1, 0. And this last one would be 0, 0, 0. Just like that. And then 1's in every other spot. So you see it's the exact same equation that we had last time. And then here's just kind of one more example. So on the last ones, these were kind of examples where every single term went to exactly 1 square. So this example is kind of different. So this is an SOP. So we're looking for like, when does this equal 1? And so that happens when both A and B are both 1s. So if we look at this region, this whole bottom region right here, this is all A is 1, and this half of the rectangle is when B equals 1. So they overlap right here. So both of that's A and B equals 1. And then for this one, not B and C. So we look at the not B region ANDed with the C region, and that gives us these 2 squares. And then this last one, A, B, and C. So that's this one right here, which we already had. And then zeros go everywhere else. And then, of course, you just do your normal looping, and we're done. So any questions on kind of going from an equation to a K-map on any of these?
Would you also have 101 and 101?
Which one?
101 and 111. Would you have to loop those as well?
These?
Yeah.
Right here?
Mhm.
So you don't have to, but as we'll see later, this is one way to eliminate glitches from your circuit. So you wouldn't have to do that for the circuit to work, but this would eliminate glitches by doing that, and I'll get to that later. But as long as all the ones are circled or all the zeros are circled, you're golden. That's all you need to do. So now moving on to don't cares. So don't cares, we can use them as a 0 or 1. And so kind of whatever makes your life easier, you can choose them as. So like in this example, they made the don't care 0 right here. So the POS is just a super simple loop like that. And the SOP would be those 2 loops. And then this one, they made this one a 1, just so their loops would be as big as possible. And the equations, they should match up well, they don't have to. This is just kind of a coincidence that they happen. And here's another example. So in this one, they made this guy a 0. And that was just so they could make the loops as they did, kind of as big as possible. So kind of up to you, but any questions over don't cares? Okay, we'll move on to entered variables. So there will be like a simple entered variable problem on this exam, something like this top one. I doubt it'd be something like the bottom one, but most likely something like this top one. And so the idea is if we had like a truth table like this, we can kind of get rid of this whole D column and then use D in our output. So if you look at, like if we kind of break this up into lines like this, then this first part goes to this row. This one goes to there, because we see like the output is dependent on D, right? If D is a 0, the output's a 0. If D is a 1, the output's 1. So you can just construct a new truth table like this kind of by combining these two together. Then you get your K-map. And so one other thing to note is every time we do like one entered variable, our K-map shrinks by half. So like before we had like a 4x4 K-map with this truth table, but this one's going to be just this 8-cell one. And then if we simplify it even further, we get down to a 2x2. So I have an example for that. So my favorite way of doing this is how like I learned how to do it when I took the class from my TA. And he told me to picture like the entered variables as like a miniature K-map. So if you can imagine, like if this is like a 1x1 K-map for D, so let's say this is D, right? So D is either a 0 or a 1. That's all it could be. And so I just can, whenever there was a D, I put a 0, 1. And then the zeros are just 0, 0, and the ones are 1, 1. And then I just make my loops. So like this would be my first loop, like that. And that equation, so we see that A is always a 0. And so this one would be A0 and D for this first loop. And the second one, I would do something like this. So this one would be, it looks like B and C for that one. B and C. Something like that. Okay. And so any questions on how I did that?
You didn't include D because you didn't use it, right?
Yeah, I didn't include D because I circled both terms here. So that's why. If I only circled this bottom term like that, then I would have to include D there. But I didn't. So that's why. So on this top one, you see I only circled the bottom part, which was like the D. And so that's why I'm including it in the equation. And so, yeah, here's the answer key. So hopefully I did that right. A0 and D or B and C. Yep. Okay, so I did that right. Cool. So here's like the POS version of it. So you're looking for the zeros. So this whole top one is kind of this term. So yeah, this one goes to here. And so you see A is a 0 and D is a 0 this whole time. So just kind of following by example, that's how you do that. And then the other terms are all like normal K-map stuff because there's no entered variables in there. So any questions on K-maps? That's kind of all I had for K-maps.
So for that, is your goal to, like, if you're doing max term there, is your goal to like get all the zeros circled?
Yes. So what I do here, so like if I was to do this again, let me get blue. So this would be my first loop, and this is the A or D, because A is always a 0 and D is always a 0 in this case. Then this next one looks like, so I'd circle all the zeros, and so this would be A bar and, well, or with B on that one, and then this last one you'd wrap around like that. So this one would be the A bar or C.
Okay, I wasn't sure if you double, like, since there are 2 zeros, do you have to double count it or something?
No.
Okay.
So this is the same thing as like a normal big 0 in there, just like
Okay.
right here. You see like the big 0.
Yeah.
So I'm just making it a little more explicit for you, so you kind of see that no matter what D is, the output is a 0. So that's why we don't include D in the equation, because it doesn't matter what D is to begin with.
Got it. Makes sense.
Quick question.
Yep.
So at the 110, if we had a D there, how would you loop that?
Oh, so this is the D right here? No, sorry, 110, my bad. Let's see. Erase it. So 1 so 1 1 0. So in this very bottom one.
Yeah.
Okay. So that one. So if this is a D right here, then this would be a 0 and this would be a 1. Right here, let me just start over here. So this is a D, right? So this would be a 0 and this would be a 1 down here. And so if I'm doing let's do the SOP first. So SOP, I would do this bottom part. And then on this one, I would do this. Oh, I would do something like this. And then I'd have one more circle. I have this one like that. And so this very bottom one would be A and B and D. And so
couldn't you do a loop where you
I
have
could do
like a
this one.
square on the, and then you just have a 2?
Yep. So
All right. Okay.
you could just write, so yeah, using the don't care, you could do that. So you can just write B and D. Good catch.
Yeah, that was my question.
Okay, perfect. Yeah. You guys are going to do better on this exam than I would. So, so let's go to.
We'll see. We'll see. We still got the second half.
Okay. So, yeah, multiplexer. So, I like to think of this as like a digitally controlled switch. So, depending on what the select input is, a 0, 1, 2, or 3, then we kind of move an imaginary like selector and get one switch. So, here's like this is just a normal SOP circuit right here for making like a 4-input mux. And so one application of that is that we can make kind of any circuit we want. So if we're given like this description that, hey, when A and B are both zeros, then G is a 0. So we just tie I0 to ground. And so when A and B are 0, the select is a 0, so I0 is connected to G, right? And it's hooked to ground. And so same thing here. A is 1, B is 1, G is 1. We just connect it to ground to VDD. And then A is 1, B is 0. We can connect it to not C. And then when A is 1 and B is 1, we can connect G to C and D. So that's just kind of an example of how you'd use a MUX to implement some combinational logic without doing any K-maps. So this would not be a minimized circuit. This would just be a simple circuit that would work. So any questions on that?
No, just got to practice on that one. I messed up on last exam on that one.
Okay, yeah, so just go through it, and like if it's like multiple choice on this one, just make sure that the select inputs match up with the corresponding values. That's kind of the biggest thing. So like if
So
we
if you flip the order of the A and B, does it just reverse all the outputs?
not really. So let's pretend this is B and this is A, right? So when A is 0 and B is 0, there's no difference. So this would be the same thing. When A is 1 and B is 1, this would be the same thing, but these two would be flip-flopped.
Okay, and so if you wanted to have the same output as the previous version where you had them swap, you would just need to switch I0 and I1.
Yeah, so I'd switch to I1 and I2.
Or sorry, I1 and
yeah,
I2.
yeah. So if you switch those two around, then yeah, you'd be able to do that.
Okay, sweet.
Okay, so moving on to decoders. So have like if they have like n inputs, they have 2 to the n outputs. So that's one thing to note. And the pretty, so you just input like a binary number. So it's like binary 0, binary 1, binary 2, right? All the way down to binary 7. And in this one, like bit 0. So bit 0 is a 1, and this one bit 1 is a 1, all the way to bit 7 is a 1, and all the other ones are zeros. And so you can also use binary decoders to do min-term circuits, so like SOP. So let's say that we had like a 3-input, 2-output circuit, and this was how it was described. So this is like if we had like X, Y, Z, right? And then we have S and C, like that. And then we had all the different 8 things there, right? Then we had a whole list of things here. So if these are the min-terms, then we can just hook OR gates up to the output. And so this is the exact same kind of concept as the SOP, because like, let's say the one output is a 1. Then if that's a 1, then this guy's a 1 there, right? And on like 5, if this guy's a 1, then we have a 1 on the output here. So if S is any one of these, well, let's say our inputs were that. So if it was like X, Y, Z, right? Then like a 1 would correspond to like a 0, 0, 1. And so this guy would turn on in that case, and then make the output S be that. So any questions on using a decoder to make a circuit?
What would be the case where S or C is a 0 in that?
So in this one, this guy would be a 1, right? All the other ones would be zeros. And so this would have all zeros right here, right? These are all zeros, so the output is a 0. This guy would have all zeros as input, so the output would be a 0.
And what would X, Y, and Z equal there? Just
Oh,
sorry.
0, 0, 0, 0, 0.
Okay. Thank you.
Yeah. So going on to priority encoders. So this is like the opposite of a decoder. So we have like 2 to the n inputs. I'm just talking about these inputs right here. And then we'd have n outputs. And you don't worry about this one. This is if you want to make like a massive priority encoder with smaller ones. We're not going to do that, so don't worry about it. And so it's like the total opposite. So if you hooked up a decoder to an encoder, then the inputs to the decoder would be the outputs of the encoder. So like, here's the first example. So if our input to this guy is 0010, so like this, right? 0010, we see that this is, so bit 1, this is bit 1 is a 1. So the output is going to be a binary 1, like that. And then in this one, we see bits 3 and bit 1 are both like high. And so we always take the highest number. So that's where we get this. This equals, yeah, that equals 3 on an output. And then kind of the corner case is, what if they're all 0? In that case, it doesn't really matter what we make y, but we're gonna like set this error bit high just to show that there was like a legal input, because if we have like 0001 as our input, then we would output like y equals 0, and the error would be low because that's like a legal output. So they're called priority encoders kind of because of example 2. That's where they get a name from, is because this higher bit has priority over the lower bit over what the output is. You could make like a priority encoder where it would use the least significant bits to make an output, but most of the time they'll be like this. So any questions over that? I don't think this is going to be on the exam. I'm just kind of covering it just in case.
I honestly cannot digest this one. So I see inputs, and it looks like we have 8 inputs. But on the example 2, under example 2, it looks like we have 4.
Yeah,
I'm not
so
sure I follow.
This is my bad. So I have like an 8 to 3 encoder. This is actually a 4 to 2, and all the examples use 4 to 2. I just could not find a good truth table that showed a 4 to 2. They were all 8 to 3 for some reason. So you can just do this. Ignore this row. Ignore all of this. So ignore that. And now it's I should have just done this earlier. So now it's how we want it. So instead of I, this is like D0, right? D1, D2.
Oh, okay. That makes a lot more sense.
Yeah, my bad there. And so, yeah, we're just looking, I guess, yeah, this wouldn't matter either. All these, know that too. So we're just looking at this kind of section. So yeah, if D1 is a 1 and the other ones are zeros, then that's the output. If D3 is a 1, it doesn't matter what the other ones are. The output's going to be a 3. So that's all it's saying. And then I added one more thing, which was if they're all a 0, that one's not shown here, then you would say there's some sort of error that's going on. And then, so here's like an example, just from one of our projects of like a transmission system, just using a mux. So like the mux is selecting exactly one of these data points. Then it's going over here, then getting decoded on the output. So you'd use this in some communication system. Let's say it was like $1 million to run a piece of wire from here to Spokane with like all the different like relays and everything. Maybe there's like a telegraph system. And so you would not want to run 8 lines in parallel if you didn't have to. So this is one way to get out of that. So that I think that was on the first exam. It might be on the second, I don't know. But it just kind of shows a different part. So the count is just counting 0 to 7, 0 to 7, selecting input 0 to 7, and then the decoder is just outputting those values on here. So like in some real life system, you'd probably want to like memorize this output and then store it somewhere. But that's not critical for the exam. So that's just kind of an example. There's not really a lot to take away from there. Just understanding like when a mux is used, like when a decoder is used, what a counter is. Counters are going to be very important on this exam. So just understand. I guess we'll just cover that right now. So like the counter, this is like a 3-bit counter. And so if it's a binary counter, it's going to count from 0 up to 2 to the n minus 1. So this is like 0 to 7. right? And if we had like a 15-bit counter, well, let's say we had a 16-bit counter. So 2 to the 16 is like 65,536. So a 16-bit counter would count from 0 to 65,535. And then it would reset to 0. So that's a counter. And then a BCD counter, that just counts 0 to 9. So that's like, it's 4 bits, but it uses a reset. So any questions on counters? Okay, let's move on then. So
Do we need a clock divider for counters?
So it depends on the application. So let's say like, if this clock input, let's say this is like 1 kilohertz already, then we wouldn't. So you can use a counter to make a clock divider. But this clock could be 100 megahertz. Doesn't really matter what it is, as long as the system can handle it. So most of the time in 214, like if you're making like the stopwatch, for example, you're going to have a clock divider coming in here to give you a 1 kilohertz input into like a BCD counter. But the actual clock divider is really just a counter in itself with a little extra functionality, and that's running off 100 megahertz. So you don't need a clock divider to run a counter.
Okay.
So shifters. So I just wanted to point out kind of this operator right here. This is like the left shift, and you also have the right shift. And so like what it does is like a left shift 2, you take like the bottom bits and you slide them over. And when we do that, that's where we have this right here. And then we just fill them in with some fill values. So by default, it's a 0. We could have made that a 1 by putting some more logic in there. But if we wanted to do something like this right here, this line, that's what it's doing. It's shifting everything over 2 and filling in the extra bits with a 0. And then a rotation, it's kind of the same sort of concept. So we're going to take this guy and we're going to slide that over. But then we're going to take the upper 2 bits and we're going to put them at the end like that. And so that's where we get this from, which is the same as up above, but then the last 2 are different. So any questions on shifts and rotates?
So how does it work when you stack like direction, rotation, and fill? Like what's the order? Does it matter which order you do them in?
It doesn't matter. So in Verilog, you're going to have like a bunch of if statements, right? So like if direction is 1, right? Then begin. It really doesn't matter. Play an else, but then you can have like internal stuff here. So it doesn't matter what you do it in. The way I would do it is I do probably like, is it a shift or a rotate? Then is it direction up or direction down, like a 0 or 1? If it's a shift, you don't even have to like pay attention to how many you're shifting by, just because this operator will handle it. You could have said shift 4 and it will shift 4. So you're gonna have to have like 3 layers of if statements pretty much, because you have to specify what direction. You'll need to specify like the number you're gonna shift by, and you'll have to say shift or rotate. So we'll call that like R. So I'd be surprised if this one came up on the exam because it wasn't on the last one, but you never know.
Well, I remember a question where we had to document the behavior and we were given an input and it was that we got control inputs for fill and rotate, I think, and we were supposed to shift the bits.
Yeah, and then we also had to code a Verilog code that does it.
Yeah.
Oh, right. Yeah.
So
That was
that's
horrendous.
yeah. So that's like straight out of project 5, I think. That's one of the requirements. So if you did that requirement, then you can just copy paste that and you're good. But if you didn't, you're gonna need a bunch of. If we have some time at the end, I can come back to this and show you like an example of how to code that up. but this is like how you'd shift left 2, and this is how you'd rotate left 2, just as an example. So you see like the bottom 6 bits right here. This is the bottom 6 bits. I'm putting those on the upper 6 bits of the output. And right here, I'm saying the upper 6 bits of the upper 2 bits of the input, which is like these, those go to the bottom 2 bits of the output. So using something like this, you can make like any rotator you want. And then these diagrams, they don't correspond to any of my examples. That was just off Real Digital. So you can see the difference between different types of like rotations. So that's kind of everything from the old material. Is there like any questions over that? That's kind of all exam 1 stuff. Okay, well with that, let's move on to new stuff. So delays. So delays happen just because of resistance and capacitance on wires. They can't travel at the speed of light just because of those like restrictions. And so if you want to know more about exactly how they're affected and what the waveforms look like and all the transient behaviors, take 351. That was an awesome class and I really enjoyed it. It's really math heavy, but it's pretty cool because you get to model lots of really cool things. So all I wanted to say about delays is that they are what make glitches possible. And glitches can be either very bad for a system or they won't really matter for a system. So like, here's an example. Like, let's say I have like this IP block that I made and it's going off to an LED, right? And that's going to ground. So in this case, let's say there's like a glitch that's like 1 nanosecond long in duration. Like the human eye can only see it like 60 hertz, maybe 100 hertz. And this is 1 gigahertz, this glitch. So your eye is not going to notice that. So in this example, a glitch would not matter. But let's say you had like some important like ROM right here. So this is like a ROM memory, and you had some like reset signal hooked up to here. You do not want a glitch ever to be on this reset signal, because if that's asserted at the wrong time, you might delete all the data inside your ROM, which would just be catastrophic and so annoying to debug. So glitches can be bad, or they can not do anything, but I guess they're not good, but they're to be expected. And so here's an example right here. So right here, like, let's say that A is a 1 and C is a 1. We'll just keep those there for the whole time. So in this example, we'll have like A and B naught, or C and B on Y. So we'd expect Y to be a 1 at all times, but because of this little delay right here, it causes a glitch to happen right there. And that's, so let's say, so B was like a 1 right here. So B goes from 1 to 0. So if B is a 1 right here, then we'll have a 0 here, right, and a 1 there. Just kind of steady state. This is a 1, this is a 0, that's a 1, right? But then let's imagine that changes. So let's say, so as soon as B changes, oh, sorry. I don't know what happened to my pen. So let's say B immediately goes to a 0 right here. So we're at this point right here, right? And so what's going to happen is that this is immediately going to be updated to a 0, and then that 0 is going to get propagated out to here. But this one, it was a 0 before. It's going to still be a 0 for tau 1 second. So maybe this is 1 nanosecond. And you can just imagine these are all 0 nanoseconds if you want tau 2. It doesn't matter what they are as long as they're different than T1. I think they have to be shorter than T1, or it might not matter. But for this one moment, we're going to have a 0 there. So a 0 there, and then 0 or 0 is 0. So that's what causes this, what's called the negative glitch. So any questions over why glitches happen?
I don't have any.
Okay. Then bonus points for anyone who can tell me what this circuit is. Right here.
Is it XOR?
Nope.
Okay.
This is a 2-to-1 mux right here. So that's just a little thing to note that might help you on the exam or not. So because you can see like B is a select signal, and then depending on what B is, it depends like if A gets propagated through or C goes through. And so let's talk about eliminating glitches. So whenever you have two circles in your K-map that kind of are adjacent but not overlapping, they're going to create what's called a coupled variable. And what happens here, like you see right here, B is changing from a 0 to a 1 or 1 to a 0. And so B is coupled. So that's why we had this glitch right here. So that's exactly the circuit that we have right here. And so that created the glitch. But if we put a circle around the coupled term like that, then it eliminates the glitch. So here's a quiz for you guys. Someone can just chime in. So how many, like which ones of these are going to have glitches on their outputs?
The
I'm gonna
first,
say two of them.
first
So which
one.
ones?
The first one and the third one.
So this one is, this one isn't. The third one is not going to have any glitches because these are not adjacent. So you see in this one how the blue, this circle and this circle are like right next to each other. That's going to cause a glitch. In this example, they're separated by a row of zeros, so there's going to be no glitch. So one thing to watch out for, let's say we had something like this, a 1 and a 1 like this, right? And this guy was circled. Now it would cause a glitch because this one and this circle are adjacent to each other, kind of just because K-maps can wrap around. So this would cause a glitch in that example. But that's a little technical. So you got to watch out for that too. And so like over here, that's not happening. Well, there's a glitch here, we know that, but I think that's the only glitch that I see. Because like these guys, they wrap around to that side and they're fine. This one wraps around down here. That one's fine. So just be on the lookout for that. There might, if there's some tricky question, then this would cause a glitch, even though it doesn't look like they're next to each other.
Can don't cares cause a glitch? Like if there was a don't care at 0, 1, 0, 1 and number 3, would that cause a glitch?
So it doesn't matter if they're entered variables or don't cares. It's all about, are the loops adjacent to each other?
Okay.
So if the loops are adjacent and they're not overlapping, then they will cause a glitch. Or they have the potential to cause a glitch. And so in this example, like to eliminate, oops, my bad, to eliminate this glitch, we would just put a circle there. Then, I mean, the equation for that would be what? Looks like A and B don't change and D doesn't change. So like A bar or B or D, right? Something like that. And that would eliminate the glitch from whatever circuit you had if you added that term to your SOP.
Does this apply to
So,
POS as well? Same exact thing.
yeah, same exact thing with POS. So if you had like some zeros, like let's say you had like this, and this is a bad example because you of course wouldn't make this, but this would have a glitch right here. That's a glitch. So if you can, make an extra term and circle it. So any questions on that, eliminating glitches or detecting glitches in a K-map? Okay. So I'm going to move on to basic cells now. So a basic cell is kind of the most primitive memory device that we can create. And so they can just memorize a 0 or a 1, depending on set and reset. And so we can make them out of two NOR gates. So this is a NOR gate, right? This is also a NOR gate. It doesn't look like one, but if we make it an OR and we flip the bubbles, then you'll see it is a NOR gate. And so on this one, the inputs are asserted when they're high. So all that means is like if we hit reset, then we're gonna, so let's say reset's a 1, then reset is like asserted, right? It's high. And in this example, they're asserted low. So when reset is a 0, that's when they're asserted. And then if set and reset are both not asserted, then it's just going to hold its value. And sometimes you can get some like astability with these. If like you assert, I think it's if you assert 1 and 1, then you can actually get metastability, which kind of moves us on to the next circuit, which is the D-latch circuit. So this one it's drawn like this. It's built up of these gates like that. And its job is to memorize whatever D is when G is asserted. So when G is a 1, it's going to memorize what's on D. And when G is a 0, it's going to keep Q at whatever D was when G was high. And so here's an example. So right here, G goes high. And so Q memorizes what D is, right? And you see that D changes right here, but Q doesn't care because it memorized what G was. And so when we get to this one, this is where it memorizes the output again. And it just kind of continues. And then again, right here, we have a memorize there, and this one's memorized, and that one's memorized. So you see that when G is held high, but here's a question, like let's say that I just tie this one to VDD. What is Q going to equal?
Whatever D is at all times.
Exactly. So in this scenario, like this would just be like that. This would just be a NOT gate if you just hold it high. And if you hold it low, then we don't really know what's going to happen because before we memorize anything, we don't know if the output's going to be a 0 or a 1. So any questions on basic cells or D-latches?
What kind of questions would he ask about it? Like create a D-latch, or what would it?
So I kind of covered, so there might be like a timing diagram. This is something that he likes to do a lot on his exams is he'll give you a circuit, be like, okay, create a timing diagram for this. So if you can see the circuit, be like, hey, yep, that's a D latch. I know how they work. It's just going to memorize D when G is high. And so you just go through here, and this might be a question. I don't know. I stole this off of Real Digital, but you can see that Q is whatever value it is. Then if you could take these two inputs right here and come up with Q on your own, then like you're more than good enough for any kind of question he's going to throw at you for this sort of thing. Then same with this one. If you understand the operation of this SR latch, just you'll be fine.
So now this makes a lot more sense to me. I just have a few questions.
Mm-hmm.
So let's say I hit so I know I'm gonna have a issue if I hit S and R at the same time. What is and then if I hit 1 on set, then that means it's gonna memorize whatever Q is. Is that right?
On this one, on the basic cell?
Yeah.
So it depends if you have a NOR or a NAND. So on the NOR, it's reset dominant. So what that means is that if you assert set and reset at the same time, so it's this bottom row, then it's going to reset. If it's a NAND basic cell, then it's set dominant. So that means that this set signal kind of gets priority over the reset. So let's say, so this is the example when they're both asserted, would be when they're both 0 in this case, because it says asserted low. And so in this case, we're going to set. And so set just means so set means that Q equals 1, and reset means that Q equals 0. So it depends on if you're using a NOR cell or a NAND cell, what's going to happen.
Okay, and then what is QN?
Oh, this is just, so QN is just not Q. Not Q. QN is not Q. So if this is a 1, right, this is a 0. And I guess that's not true in this case when they're both asserted. But yeah, typically they're going to be the opposite. So this is kind of, in practice, one of them is always going to be on, the other one's going to be off. You're not going to really run into the scenario where they're both asserted. So you see, in that case, they are the opposite. So I guess I shouldn't say that. So that's it. You don't necessarily have to have a Q naught in there. That's just kind of one of the outputs.
Thank you.
Okay, so D flip-flops. So this is kind of the D latch. So the D latch is just looking at whether G is high. In a D flip-flop, it's going to memorize D on the rising edge of clock. And so like this means rising edge, that symbol. If it was drawn like this would be falling edge. So if it said like clock like this, so if this was a circuit, this would be falling edge. Those are pretty rare, and you might even see like something like this, where it's, I can't draw this. It's like this shape. This means like dual edge. So rising and falling edge it would memorize. So yeah, I think these are even easier than, I don't have an example waveform, but it's the exact same thing as this guy. So you just look for, let's say that if G was like the clock, then you'd only look for this scenario when that goes on the rising edge, when this one goes on the rising edge, and when this one goes. So in this case, if this was instead a D flip-flop, then Q would not go high like this. It would just stay 0 because it's only memorizing on the positive edge. So any questions on D flip-flops?
So only on the instance that the clock goes high.
Yeah, so
So
unless
it
it's-
would be really tiny like blips for Q in that case. Like at 0.1 and then at 0.3 for the previous graph.
It's gonna memorize it and then hold it high. So like just like here, so pretend this top one is clock. So it's gonna memorize what D is. So D is a 0 in this case, right? So the output Q is gonna be a 0 until we get to the next rising edge. We look at the next rising edge and we say, oh, what's D? Oh, D's a 1. So Q is gonna be a 1, and it's gonna stay a 1 until the next rising edge of clock, which happens here. And so when we look at this rising edge, then that corresponds to a 0 here. So this is going to be 0. And because there's no more rising edges, it's just going to stay a 0. And so
Got it.
Q is not going to be up for just a blip. It's going to be up. Normally this clock would be like, let's say you had like a 10 megahertz signal. Then, I mean, the shortest blip you could have would be like 1 period, which would be 100 nanoseconds. Kind of minimum time. So JK and T flip-flops, I don't think this will be on the exam, but just to cover it. So with the JK, the J sets, and when I say sets, I mean it makes Q a 1, and K is the clear, and all these happen on the clock edges. So like right here is when these actually take place. So you'll see that, hey, J's a 1, so we set it, right? And then K is a 1, so we reset it. And then here, nothing happens, so we just hold it. And then here, looks like J and K both go high, and we're going to a 1. So that looks like it's like J dominant in that case. And the T flip-flop, that means toggle. So if T is asserted, then Q is going to toggle. So based off the last state. So if we reset it, right, the reset makes that a 0. Then we say, oh, we need to toggle here. So it goes to a 1. It's like, oh, we still need to toggle at this point. So it goes to a 0. And then we don't have to toggle here because at this point, T is a 0. So this stays a 0. And then on this one, it says, hey, we need to toggle again. So it goes to a 1. And then this one, the toggle's a 0, so it doesn't toggle. So any questions on that? JK or toggles? Okay, so moving on to registers. So we can use D flip-flops to build up registers. And these have like so many different uses in digital design. So the most common one is your PIPO. So this is like the keyword reg. Like let's say you did like reg 3 to 0, like count, right? That actually creates a PIPO register when you do that in Verilog. And so we have other different flavors. So like the SISO, this is the serial in, serial out. So it takes only one input. And so let's say like this is a 1. And so if we put a 1 there, then after one clock cycle, this one's going to propagate to here as the input. And then after the next clock cycle, it's going to move there, and then move there, and then move there. So if you guys are into like Arduino projects and stuff like that, you sometimes use shift registers to like, you can drive a 7-segment display, for example, with one of these if you really wanted to. Although SIPO is probably a lot more useful. So the SIPO, this is like a USB kind of driver or like a 5.0 chip. So let's say we have some crazy like 100 gigahertz signal coming in, right? And then we had a bus, but the bus could only run at 250 megahertz. What we would do is this data would come in bit by bit. So if it was like a 0, 1, 0, 0 across 4 clock cycles, then we'll have a 0, I guess, yeah. So if this is a like time 3 and this one's like time 0. So time 0 happens first. So like a 0, 0, 1, 0. And then we could output this on the bus all at the same time. So that's kind of the purpose of that one. And then here's a piezo. So this is very similar to the CISO. You see like the feedback loop right here, or like the feed forward loop. The only difference is that we have these muxes added that allow us to either load serial data in or parallel data in. So you can use a piezo. So a piezo like works as a CISO as well if you set parallel load to 0, yeah, because then it's always going to load in. Otherwise, it'll function differently. And then, of course, this is the universal one. So this one can implement every single type of register. So PIPO, SISO, SIPO, or piezo. So I'd expect a question like that on the exam. That was, I think it's been like every single exam he's ever had. So
Wait,
any questions on these?
what would the question be? Like, what would it entail?
Oh, it'll be like, what, well, I don't want to give too much away. Just understanding that a universal register can like implement other registers, and like knowing which ones can implement the others would be a good thing. So just recognizing like, hey, like this one right here, like a CISO and a SIPO, or SIPO, they're like the same thing, but you can just add a wire here. So like if I only had a SIPO chip, but I needed a CISO technology, then I could just buy one of these and use this one and use it as a CISO. So that's all it's asking. And like for this one, you could use it as all 4 of them. So there's everything built into it. So any questions on that? So this is all kind of D flip-flops, memory cells, and registers. Any questions over that stuff?
So could you use a pipo like a piso? Is that the same thing as well?
So no, you can't, because you'll see that there's no like feed forward loop. So in
Okay,
the
I got it.
with all the serial out ones, you have this kind of weird branching thing, but that doesn't exist in this one. That's actually the only one where that doesn't exist. But yeah, good question. So I'm going to move on to 2's complement. So 2's complement is used for binary numbers. So if you wanted to have negative binary numbers, then you need like 2's complement or some other form and some custom circuits. But we always use 2's complement in like 100% of the case. So normally with like an 8-bit binary number, right, we could go 0 to 255. So unsigned just means that it's always positive. So like greater than or equal to 0 is what unsigned means. And so that's great, but if we want to represent negative numbers, we don't have a way to do that. So we used signed like binary numbers, or like they're called 2's complement numbers. And so they give us a range of like negative 128 to 127. So that's just, if it's 8-bit, then yeah, negative 2 to the 7 to 2 to the 7 minus 1. So same number of binary numbers. You have 256 different options. They just kind of move the range around a little bit. So then they're useful with subtractors, because adding like a 2's complement number is like the same thing as subtracting an unsigned number. So here's an example. So like, what is negative 12 in 2's complement? So we'd write 12 in binary. So like this is the 1's bit, the 2's bit, the 4's, the 8's, right? So 12 is 8 plus 4. So, and then like this is a 16, right? Blah, blah, blah. And so this is what 12 is in binary. So we're going to flip all the bits and add 1. So we flip them and we add 1. Like we'll get like 1 here, right? And then 0, carry the 1, 0, carry the 1, right? And 1. So that's how I got this number right there. And then if you were to add these 2 numbers up and just kind of start carrying the 1s, you would see that you get this number. And because we don't care about this number, it just falls off and we get 0 as our answer. So that's kind of how you do it by hand. I'm going to show you how to do the exact same problem with Windows Calculator. So let me make sure I'm sharing my entire screen. Okay. I'll keep them. So Windows has like the calculator app, right? And if you press this button right here and go to programmer, then it has all these awesome options for you. And so you can like enter any number you want, right? Like 47, it'll tell you what it is in hexadecimal, what it is in decimal, what it is in octal, which is base 8. So this is base 16, base 10, base 8, and binary, base 2. And you can do like different and, ors, whatever you want. But the best thing about it is like, if I had like, let's say if I wanted to do like negative 12, I can just type in negative 12 and you get a binary number. And so this is too big. So we'd click this till we got down to byte. So this is like a 4-bit word, 4-byte word, 2-byte word. Sorry, this is 8. This one is 4. This one is 2 bytes. This one is only 1 byte. And so you see right here that like that is a negative 12 right there. So if you had a question like, what is like, let's say 18 minus, I don't know, 25, then I mean, it's negative 7, of course, but then you also have the binary number. So I encourage you guys to use this to check your work. And you also have this mode, which lets you like flip the bits individually, which is kind of cool. You can see exactly how they change. And if you have Mac, I'm sorry, I don't know how that works. So get back into this. F5. So here's an example, right? So I'll just do this one by hand. You can just use the calculator normally. But I get 5, right? That's not 5. What am I doing? This is 5. My bad. So that's 5. This one is 7, -7. And so if you add these guys up, then you get like a 1, carry the 1, 1, 1, 1, 1, 1, 1, 1. And if you put that into the calculator, you'd see that equals -2. So any questions on 2's complement or subtracting numbers? All right. So we'll get into adders. So we have 2 different kind of flavors of adders. We have the ripple carry adder, and we have the carry look ahead adder. So the ripple carry adder is kind of the simplest design. We use what are called full adders to add 3 numbers. We're adding some like A input, some B input, and some carry input. And so here's a schematic for it. You can build it with 2 half adders like that. And what happens is we'll compute this value, we'll get the C out, then this C out will get passed to here, right? And then they'll just propagate. And the problem is that that takes a bunch of time for it to happen. And so you can imagine like if we were computing like 64-bit numbers, it would take 64 of these jumps to get to the very end. And so that could be a problem in like a high-speed system, like an ALU for like a microprocessor. You do not want to wait on 64 of these things to happen. And these might take 1 nanosecond each because of like gate delays, right? And so if you had to wait 64 nanoseconds, that is way too long because 1 clock cycle is only 10 nanoseconds. So this is kind of a simple design. It works, but it's not good for high-speed systems. So they invented the carry look ahead adder. And so what this uses this kind of this circuit down here to identify what all the carry bits should be at the same time. And so this is all off real digital, pretty much everything is. And you can just see how each carry bit is computed. It's just like the previous carry bit and this p-value. So if you have any questions on that, just look at the real digital thing on that. So any questions over these 2? All right. So yeah, the biggest thing is that this is faster. That's the biggest thing. This is why you'd use it. It is more expensive, uses more gates, but like UFPGA could literally put millions of these things on there with no problem. So that's not really an issue.
Would we have to do something where we would have to simulate like a 4-bit addition, or?
So maybe by hand, you wouldn't have to do it in Verilog.
Okay.
So if you can just understand like what's happening here. So that's okay. I'd have to look at the real digital site to confirm what these were. These are basically full adders right here. So let's see, what does propagate equal to? P0. So okay. So I'm just going to move on to the next one real quick. So subtractors, we have 2 types of subtractors. So we have the ripple borrow subtractor. So this is like the ripple carry adder. I should say ripple carry adder. And it has the same issue as the ripple carry adder where you have to like get every borrow bit from the previous bit slice design. So they also have like the carry look ahead subtractor. I've never seen it, but I'm sure it exists. But what everyone uses is they just use 2's complement and an adder together to make the subtractor. So like this would be like a B minus A subtractor right here. So it's using these XOR gates as controllable toggle switches. So remember with the XOR gate, right? If we have, let's say that this is like X and this is Y. So one way to, the output right here, if Y is a 1, then the output is going to be like not X. And if the output is a 0, if Y equals 0, then this output is going to be X. Just because if both of them are asserted, then it's going to toggle it. So you'll see something like this to make a subtractor. And then, so this flips all the bits, and then we add 1 with this input right here, with the carry in. So that's literally, this is the whole 2's complement algorithm. We're flipping all the bits, and we're adding 1. And so that's when sub is 1. When sub is 0, then the XOR gate, when like let's say if Y is 0, or better yet subtract is 0, then the output's just going to be an X. So it doesn't do anything. This input would be a 0, so nothing would be added, and you'd have your normal 8-bit adder. So this is like the adder and subtractor. Any questions over that?
You said when X is a 0 or Y is a 0?
Okay, let me just redraw this all. So my point was like let me redraw it with like the subtract signal. So let's call this like A, right? A0, and this is subtract. So when subtract is a 1, so let's say this guy is a 1, then the output is going to be not A0. And when this sub signal is grounded, then the output's just going to be A0. And so by changing what subtract is, we're inverting the output. So that's why I say it's a controllable toggle switch, because depending on what we make sub, we can change whether this output is a 0 or a 1.
That makes sense. Thank you.
Yep, and then you might see it drawn like this. This is just shorthand for that. Multipliers. So the way multipliers work is they use this network to make what are called partial products. And so you'll see like this is a 4 by 4, 4-bit by 4-bit. So we'll have 4 over there, 4 over here. So we'd have 16 AND gates in that network. And of course, like if this was like a 4 by 10, we'd need 40 AND gates in this network. Then, so to make that, you would compute all of the different partial products. Then you just have a bunch of different full adders, and they would just kind of propagate in there. Then this is an adder at the very bottom. So any questions over multipliers? Okay. So moving on, this is kind of the last part of the class, which is state machines. And this is probably like the most important part, I think, of 214, just because it's so powerful. Like every computer or processor that you'll ever use is basically a state machine, just with some more fancy things added to it. And so you need to know what all the different building blocks are called, definitely. So know that this is a next state logic. Know this is the state register. This is the present state bus, the next state bus. This is the output. These are like inputs right here, outputs. These are called Mealy inputs, these two right here. And so we have what are called Moore versus Mealy state machines. And all Mealy means is that you have these inputs are fed back into the outputs. So basically the outputs are a function of the present state and the inputs. So that's why it says Mealy inputs produce conditional outputs. That's why it says that. So with the Moore model, these mealy inputs don't exist, and so all the information is encoded in the state register and subsequently the present state bus. So because of all of that, the Mealy model uses less states than the Moore model in general, just because we can have all of the different outputs encoded with less total states because we're using our inputs as well as the current state to drive the output. So any questions over this diagram or Mealy versus Moore?
So the difference is those two wires.
Yep, that's the difference. That's literally it.
Okay, thank you.
So let's go to, one more thing here. How many total states can we have with this state register?
I'm gonna say 4.
I'm gonna go 16.
Yeah, so 16 is the winner. So this is 4 bits, right? And so 2 to the 4 is 16. So that's where it comes from. So if you had like an 8-bit state register, you could have 256 different states in the system. And so this is actually called a binary coded state machine. There's other types that you'll see in 324 if you take that class, but this is kind of this one's very commonly used just because you can have so many states for a very small number of registers. So moving on to state diagrams. So these guys, yeah, they explain the behavior of the state machine. So they cover what every single input and every single output will be at every single state. So here's another question. Is this a Mealy or a Moore state machine?
It's a Mealy.
So this one's actually going to be a Moore because the outputs are not dependent on the inputs. Like you can see that they're hard-coded values.
Yeah, I see. I thought
So if you had something like if it was like red equals X, that would be a Mealy. But because they're all just hard-coded, we don't need any of these inputs. We can just have a decoder only reading the present state bus to give us our outputs. So this state machine is missing its state codes. And then we also have to check the sum and exclusion rules at every state. So with state codes, here we go. So binary state machine has n flip-flops. So yeah, 4 flip-flops is 16 states. So choosing state codes is kind of like more art than science. It's kind of hand wavy, and a lot of the times you can't get a perfect result, and you just have to kind of live with it. So good rules of thumb, you should always start with state 0. So reset into state 0. Try to only make 1 flip-flop change at a time, if possible. Like if you have like a loop of 3, right? It's going to be impossible for you to pick state codes that meet that. It's just because of mathematics won't allow you to do that. But if you can, try to make only 1 flip-flop changing at once. So like do not do like 0, 0, 1, 1 if you don't have to. If you have to, then whatever, but if you have the option, don't do it. So the last thing is like minimizing output logic. So if we had some system like this one right here, you'll see that a red is, so red is, well, I'm just trying to wing something. Like in this case, never mind. There's sometimes when you can make like, if this was state like, well, let's say this state was, if this state was 0, 0, right? Then the output logic would be like red equals like the state at like 1 and green is the state code at index 0. Sometimes you can get away with that. Or like if this was like a 1, 0, then yeah, so like red equals state at index 1. So meaning like this is like index 1, that's index 0. And then like green equals S at 0. So that's kind of a last thing though. You don't have to really do that. So it's more important to do 1 flip-flop changing at a time. So here's an example that I did. So you see that if we go from here to here, we have exactly one of these flip-flops is changing. When we go here to here, again, we have one flip-flop changing. If we go here, then again, we have one flip-flop changing. If we go here, we have one flip-flop changing. I couldn't avoid it here. That one I couldn't avoid. We have both of them changing. So you just kind of have to live with that and ask yourself, is that okay? And in 214, you don't really have to answer that question, is when is it okay to do that? The reason that you don't want to do that is these flip-flops will not change at the same time. So like when I'm going from 1, 1 to 0, 0, either I'm going to pass through state 0, 1, or I'm going to pass through state 1, 0 on the way to here, just because of delays in the input. So because of delays in the next state logic right here, it will cause us to go through these states differently. And so what we could have right here, we see that red is, for example, 0 right here and 0 there. So we'd expect that when we go from 1, 1 to 0, 0, that red would always be a 0. But if we happen to go through state 1, 0, then red turns on for a brief moment, and that's called an output ray switch. But that's 324 stuff, so don't worry about that. I was just kind of explain why those rules exist. So we have to check the sum and exclusion rules at every single point. So for example, so let's say we're starting at S0. You'll see, so if A is 0 and C is a 1, so that's A is 0 and C is 1. That looks like these cases. A is 1. Looks like Clint's truth table is a little bit wrong. Oh well.
Well, it should be 0, 1. The top of it.
Oh, yeah. That's what's wrong with it. I was like, something's not right. Yeah. So let me fix that. So yeah, you see those two are taken, but like we don't have the scenario for what if A is 0, B is 0, and C is 0. Like that doesn't exist, so it violates the sum rule. And then the exclusion rule is violated. Let's say that A and B are both 1. Then do we go to A or do we go to X or do we go to Y? Like we don't know. So you need to make sure that at every single node, so like at S0, for example, that we go to exactly one state for every single possible input that we could have. And that's it. That's all I have for you guys. And we did it in under 2 hours, so that's sweet.
And this is gonna be on YouTube, right? For a while.
Yes. So I'm gonna have it on YouTube until like 7 a.m. Monday.
So would you say this exam is more conceptual rather than rather than the coding?
So there's going to be probably 2 questions on the coding. So what I would do is I would brush up on your like making state machines. So if you need like help making state machines, I'll keep them. So just go on Real Digital, and they have a great example right here. So just go to 11 tutorial. Where is the tutorial? So all the way at the bottom here, here's a great example of a state machine in Verilog. So if you can understand what this guy is doing, then you'll be fine for the exam. So you might have to make some state machines yourself. So like given the description, can you make a state machine? Then once you have that state machine drawn up, can you check the sum and exclusion rules at every point? Then can you implement it in Verilog? So that might be on the exam, just because it's such a long time frame that would be kind of fair game, I think. Is there any other questions?
Yeah, I have a question.
Yeah, go for it.
Yeah, so for the state codes, when we're initializing them to like the parameters,
Uh-huh.
yeah, so we say 2 binary 00, 2 binary 01. Is that standard for every state machine?
Yeah, so the local params, this is only to help you write kind of easier to read code. You don't really need them. You could just, everywhere you see S0, you could just paste in this 2 binary 00 if you wanted to, but that's kind of, yeah, standard practice.
Okay, so even for the stopwatch project,
Uh-huh.
we're going to be having like 3 bits, right? Because we have 3 inputs.
So in the stopwatch, it depends how many states you have. So if you have 2 states, you only need you'll only need 1. So this would not, you'd only have S0 and S1, you only need 1 bit. If you had 3 or 4, then you're going to need to have 2 bits here. If you had like 5 to 8, then you're going to have 3 bits here. So like S7 might be like 2, or it'd be like 3B111, for example.
Oh, okay.
And these don't have to be, so like this is binary 0, binary 1, binary 2, binary 3. With the exception of this one, these can be like whatever number you want. So if I go back to this example right here, so like so let's call this, so I went S0 is 00, S1 is 01, S2 could be 11, and S3 could be 10. So it really just depends. What I like to do is kind of like the general flow would be like, okay, I'm going to go here to here to here to here. So this is S0, S1, S2, S3, like that. But I can assign state codes differently than that. So S3 does not have to be 11. It could be whatever you want.
Okay, it's just to like, it's like naming it, basically.
Yeah. S3 is just a name. That's all it is.
Okay.
So you're just, when you use local param, you're just defining a constant in Verilog that you can use within this module. That's all it means.
Okay, I see.
You have a good question. Anyone else?
I wasn't here at the beginning, so I apologize if this is like a repeat or something that you already went over. But could you just go over the number of transistors and like gates and inverters and stuff?
Oh yeah. Super quick. No problem. So there we go.
Okay, I'll just take a picture of that real quick.
Yeah, so inverters 2, NAND and NOR 4, and the AND and the OR are 6. So
Okay, thank you.
You can just memorize that. Anything else? Again, I am recording this on YouTube, so I'll give you guys the link to that. Sure.
Could we go back to state codes?
Yeah.
Real quick.
State codes. Oops. Which one? This one?
You passed it by 1, I think. That one, or
Okay.
that one also works. So it's always running clockwise. It looks like. Is that right?
Well,
For example,
in this example, it is. That is totally arbitrary.
oh, okay.
Yeah.
So like, just to give an example, if I hit like, if let's say X is a switch, if I hit X or if I hit the switch to turn on, let's say red turns on, and I can also have an arrow pointing to the bottom left circle when Y equals 1. Can I do that?
Oh yeah, totally. You can do like this arrow could be the opposite direction right here. This middle one. I didn't even notice that they are all clockwise. Yeah, that's actually kind of weird. I bet you Clint was just drawing and he didn't even realize that he was making them all clockwise. That's kind of funny. But
Oh, okay.
yep, yeah, they
Just
don't
wanted
have
to be sure.
Yeah, they don't. That's a good question. They don't have to be clockwise. They can meander all they want. They can cross lines. It doesn't matter. Just don't make them too confusing. All right. Well, if there's nothing else, then I'll sign off. Thanks everyone for showing up. I appreciate it. It's more fun to talk to people who ask questions than just like a blank screen. So thank you for that. And yeah, good luck on your exam on Monday.
Thank
I
you a lot
think-
for doing this.
Yeah, thanks a bunch. This is really helpful.
Awesome. We'll see you
And
guys.
Were
Oh,
we gonna go over the shift, rotate, and all that, the coding?
oh yeah, if you want, I can go through that really quickly. So let me just open up. So was this project 5?
Shifters, I believe, was project 4.
Was it 4? Okay.
Yeah, it was 4.
So this is what I wrote 2 years ago. It's probably going to be bad. So I'll fix it if it looks awful. Okay, so this is kind of what I have going on. So I have my input. This is an 8-bit shifter. So inputs, shift is the number it's shifting by. I could have said N. I have a direction, and R is like rotate or shift. So I think, and so this is what I did. I just have, here's my always statement, and I just had a bunch of nested if statements.
That looks a lot cleaner than what I did.
Yeah, this is a little sneaky, this code right here. So I'm saying, so this would be rotate left, I think. No. Which way is this? So let's do this one. So this would be.
It looks like you're putting
Right.
2 0 and you're switching to 0 with 7 3. So 7 3 is in the front now, or at least for that first if.
Well, for this one, I'm putting 2 zeros at the front and 7 3s at the back. Just because you read it left to right. So it looks like this is. See, good code has comments. This code doesn't. So I'm going to look at this example. So if I'm rotating, then my rightmost bit. So this looks like a rotate to the right by 1, and this would be a rotate left by 1. Yeah, that's right. So this is all looks like rotate lefts. These are all shift lefts, and I could have used the shift operator here. I could have just said like y equals. Let's see. So this is what? That's right. This is left. So if it's left, then I could have done like I shifted by shift, right? Or by 3. Whatever works for you. But yeah, this is kind of the general structure of a shift register. You just have a bunch of if statements, and you need the begin and end. Like if you can have up to 1 line here without a begin and end, but like if I had some other thing here, like q equals some value, right? Then I would have to put a begin. The begin and end is like, just like in C, when you have curly braces, that's all the begin and end are. So you'd have to do that if you had more than 1 line. So like if I had, then you guys all know how the ternary operator works, like this guy right here.
Yeah.
Yeah, so like if this condition is met, use that, false, do that. So,
Awesome. Well, thank you so much.
Yep. Anything else?
Well, one last question. Where are you keeping the YouTube link? Are you gonna?
I'll send that out as soon as
Okay.
this is over. It's got to like
Alright.
finish. I think it's my here. I'm gonna stop sharing, and then. Oh, I already closed it. My bad. So I will send that to Clint, and then he can distribute it to all you guys.
Thank you so much again for doing this. This was really helpful.
Yep. No problem.
Yeah,
We'll see you
thank
guys.